Hi all, welcome again in a video on quantum computing. Remember what we have done till now? We actually covered linear algebra to cover the basics required for the first postulate. What did we see? We saw the structure of a vector space. Specifically, we saw how a complex vector space looks like. What it means is that the scalars involved for the vector space are complex numbers instead of the real numbers. You might have seen real number vector spaces before. This was an introduction to complex vector spaces. And then we have matrices. Matrices are viewed as linear operators over this vector spaces. This is an important concept. We view matrices as linear operators. And we will see that there is a good reason behind it, because with the postulates we will see that our states will be vectors and then the operators applied on them will be matrices. This is a good reason to study both vector spaces as well as matrices. In the two videos before this, we saw the basics of what vector spaces are, specifically for the complex numbers, and what are matrices and their equivalents with linear operators. Now we are ready to delve into the first postulate. But what are postulates? These are statements which provide us with a mathematical formalism to advance our knowledge of quantum computing, in the sense that we say that any quantum system is going to satisfy these postulates. Using these postulates as the basis, we can build the theory of quantum computation over these postulates. For us, these are the basic laws which govern the behavior of a quantum system. These are really important, and good thing is this is all we will need from quantum mechanics. So from quantum mechanics, the takeaway would be quantum postulates. Most of the time when I introduce these postulates to students, question is, how did we come up on these postulates? How did we arrive on these postulates? Where did they come from? There is a long history. It was mostly trial and error, and then people sat together and said that it seems whatever physics we are trying to discover here, it seems to rely upon these postulates. Since I am not a physicist, I am not going to go into detail of these things. If you are interested, one of the good book is Nielsen and Chuang. This is the standard reference on quantum computing, or you are welcome to read any book in quantum mechanics and try to understand the motivation behind these postulates. For us, these are things written in stone. We believe in it, and using these, we are going to build a theory. So the question of how we arrived on it, we will ignore it, but we really want to understand what are these laws. So let me talk about the first postulate. This is going to describe the state of a system. What does a quantum system look like? Remember that this is not going to give a physical picture, this is going to give a mathematical picture of this. The first postulate says a physically isolated system. The things written in quotes will be explained later, is associated with a Hilbert space. This looks like a vector space. It is kind of a vector space, but with some extra things. Again, I will describe what they are. So first postulate says a physically isolated system is associated with a Hilbert space. This Hilbert space is called the state space of the system. This is the name given to the Hilbert space associated. And what is the advantage of this Hilbert space? This quantum system at any particular time. So you can ask, oh, at 12:29, how does my system look? What is the state of my system? It is described by a unit vector. And no surprises, what is this unit vector from? It is from this Hilbert space. And this will be called the state of the system. I have to try to write the first postulate as precisely as possible, and we will try to explain all the important terms. Let us go through these terms and see what do they mean. First is physically isolated system. In English, this makes sense. This is a system which is devoid of any external influence. That means it is not in touch with any other system. This is not really practical, but it is required because if you want to describe the state of any system, then we have to know all about it. If it is in connection with some other quantum system, then we can't describe its state. That's why in theory we say that the system should be physically isolated. In practice, we will say if it is in most situations not in connection with other systems, then we can call it a physically isolated system. If it is really influenced by another system, we will also see how to describe the combined state of these systems. That will also be another postulate. We will talk about it later. But for now, if a system is not really influenced by the system, we will call it a physically isolated system. More or less a physics term. The next thing is Hilbert space, which might be new to you. I encourage you to go and look at the formal definition of it. For us, it is nothing but a vector space. Though it is a vector space which allows us to do linear algebra, measure distances, and also apply tools of analysis. If you look at the formal definition, you will see that the vector space has some nice structure which allows us to do all these things. We don't need to go into the formal definition. We just need to remember that it's a special vector space. Actually, in our course, mostly it is going to be complex Euclidean space. What do I mean by it? It is going to be the state C to the n. It is complex Euclidean because the field is complex numbers. The vector space is over the field of complex numbers. My scalars come from complex numbers. The entries of the vectors come from complex numbers. And I am calling it Euclidean because this has this inner product. You remember, if I have two vectors x1 to xn and y1 to yn, then their inner product is summation xi star yi, where this is the adjoint operator. This is the inner product or the dot product we define. This allows us to measure distance between 2 points. It allows us to measure angle between 2 points, so on and so forth. That's why we are calling this a complex Euclidean space. It is denoted by c to the n, and most of the time our n, almost all the time our n is going to be a finite number. We remember what is n in c to the n. N is the dimension of the vector space. What does this dimension correspond to? So we said that our quantum system will be in state which is an element of c to the n, the dimension is n, we should think of n as the number of possible different classical states. This will be cleared through examples, but you remember we have a bit which was an element of 0, 1. It had two possible states, either a bit could be 0 or it could be 1. Then the corresponding vector space or corresponding Hilbert space in our case is going to be C square, one of the simplest possible Hilbert spaces. That will describe our state space. This is going to be the state space of one qubit. A bit was 0, 1. It had two states. Then the corresponding Hilbert space is going to be C square with dimension 2. And this is going to be called a qubit. A qubit will reside in C square. What does it mean? Anytime I want to talk about state of a qubit, as mentioned in the first postulate, it will be an element of this vector space or Hilbert space, C square. I will remind you, what is C square? It is the space spanned by these two basis vectors. This is in Dirac notation. Once more, this is this vector and one is 0 vector. These are not the only elements of C square. Classically, if you think about it, this state corresponds to qubit being in state 0, 1 corresponds to being in state 1. In quantum, these are not the only possible states. For bits will only exist in 0 or 1. A qubit can take any element of C square. What are any element of C square? They look like this, where alpha and beta are complex numbers and it's a unit vector. This explains one more point in the postulate, that my state is always a unit vector. Again, we will not go into detail of why it should be a unit vector. We will assume that as something written in stone. So a qubit can exist in any such state. When it is in state 0 or 1, these are classical states. But if alpha and beta are non-zero, it is supposed to be in superposition of these two states. And this is one term which you will encounter very often and consider to be the reason why quantum computing seems to be more powerful than classical computing. This is your time to grasp the phenomenon. What has happened? Classically, we had only two states, but quantumly, it could exist as a superposition. It could be a mixture. Remember, this is not same as probabilities. You should never say that this state is in 0 with probability alpha square and 1 with probability beta square. This is one consequence of this, that we will see that under some kind of measurement we will notice that this state alpha 0 plus beta 1 is going to come out in state 0 with probability alpha square and going to come out in 1 with probability beta square, but that's only one consequence of it. That doesn't mean they are equivalent. This is not same as this description. Remember that. If the state is in alpha 0 plus beta 1, this implies that it will be in 0 with probability alpha square but 1 probability square, but the opposite is not true. And we will see multiple examples which will clarify why. And we actually saw in the previous class also with this Mach-Zehnder interferometer that a probabilistic interpretation is not good enough to explain all the quantum phenomena. So this is clearly definite. Noticing this superposition, we can generalize. If we have n classical states, say a system or a ball can be in color C1, C2 up to Cn, then the corresponding Hilbert space we will take to be C to the n, where every element or the state of the Q system will always be in a state like this, where the sum of the amplitudes, so alpha 1 is the amplitude on C1, alpha 2 is the amplitude on C2, alpha n is the amplitude on Cn. The sum of these amplitude square should be equal to 1 because we will always have a unit vector when we talk about states. This finishes the description of the first postulate. We saw that the states of a system, of a quantum system, will be described by a vector. This makes us guess that the operators will be described by matrices. It will turn out that not all matrices are okay, and that will be the second postulate. But before that, we will go into a diversion. That will be the topic of the next video. Thank you.